working with the capture and compare module again. And kind of like a little review. This capture and compare module in the 18F4520, you have two of them. And they're actually labeled CCP1 and CCP2, right? And these circuits have the ability to do pulse width modulation. They can do capture. And what we're going to be doing today is the compare. And they also have the ability to do overflow, okay? So the compare mode is very much equivalent to the overflow mode. And I'm going to explain this based on, it's kind of like a timing sequence. So there is two special registers inside of this compare circuit that are going to be extremely important. If you think about the overflow, how the overflow worked, timer 1 is some sort of a counter. And this counter has just the ability to just increase numbers by 1 as time goes by, right? And so we did some mathematics behind it. If you remember, we did this T1C, which was 4 times the prescaler divided by the frequency of oscillation. And then we calculated the amount of time that it would take for this circuit to actually overflow. And that value was actually called T1F, and it was supposed to be 2 to the power of 16 times T1C. And what this really told us was that we can predict ahead of time how long will it take for this specific circuit to reach the moment of overflow. And this moment of overflow is the moment in time where the timer cannot count anymore. And then the count is going to go from its largest number back to 0, and it will begin the count again. And we said that that circuit could be connected to an interrupt vector that was called pound int timer 1. All right? So there the system is set. And so we have a circuit in overflow that has the ability to interrupt the microprocessor in predetermined periods. Right? That was the idea behind it. And so you can do all kinds of pretty fun applications with this. All right? Now, what we're going to do is that we are going to expand on this idea. And so if you think about how this circuit operates, there is only 2 variables that can manipulate the period or the frequency of interrupts, right? And one of those values is a prescale value, and the other one is the frequency of oscillation, right? One is a crystal that you actually soldered into your micro, and the other one is a value that is software variable, right? So this guy, you can change via software. Well, this guy is pretty much soldered. And those were our variables, right? Now, on timer 1, we knew that there is only 4 prescale values, which means that if I'm going to use an overflow circuit on timer 1, I can only generate 4 different frequencies, right? All right, so why is compare mode so useful? Compare mode will actually give me really high precision on the amounts of frequencies that I can generate, all right? But instead of using my overflow, I'm going to start using a compare system. You understand where we're going, right? I want to make sure that I have the ability to interrupt the processor in predetermined periods or frequencies. And I want to do that with a fine, I want to have a lot of precision to it. I don't want to have only 4 or only options. I want to fine tune it, right? I want to be able to have a really large variety of frequencies that I could use. This is where this circuit comes to play, okay? So here we go. So the compare circuit, how does that work? The compare circuit is a combination of 2 systems. There is a CCP circuit and the timer 1 circuit. So in compare mode, you're going to need timer 1 and you're going to need a CCP 1. Together, they create the compare mode circuit. All right? This is the first piece. The first piece is your timer 1. We already studied this guy a little bit. So you have your crystal, followed by a divide by 4, followed by a prescaler value, which is also a divide by, and this goes into a 16-bit timer. And this guy is called timer 1. Okay? And so for every single edge that shows up at the input of that timer, you're going to get that counter to go up by 1, right? So this guy will count from 0 all the way to 2 to the 16 minus 1. All right? Is that making a little bit of sense? So we're, in some sense, we're back to the overflow circuit. Now here's where the circuit changes. There is a register on this CCP1 called the CCP register number 1, CCP reg 1. And the CCP register 1 is a 16-bit register, CCP R1. All right? So it's called the CCP register 1. So CCP1 has a CCP R1 register. CCP2 has a CCP R2 register. Okay? Now, here's the deal. That register is a register that allows the user to give it a value very easily. So in one instruction, I can take a value and deposit it inside of that register. All right? Now here's what happens next. There is a comparator that is looking at the value of the timer and the user selected value in CCPR. When these two values are exactly the same, the machine will interrupt. See that? So you pick one value. If I deposit the value in that position, the timer eventually will hit that value. Doesn't matter which value you pick. You can pick 10. So the machine goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Interrupt happens 11, 12, 13, 14, 15, 16, 17, 18, right? The timer will continue flowing. It moves all the time. And then what you have is the moment that this value and that value are exactly the same, the machine will create an interrupt. Does that make sense? Okay, so if you think about that, you're comparing CCPR against timer 1, and when they're the same, you pound INT. Let me just clear this up and do it in the other side, but it doesn't confuse. Then this creates CCP1. See that? So notice that my vector, my circuit, the one that is interrupting is different. The capture and compare circuit is the one that says to the processor, hold it, I just compare these two numbers and they're the same. In this circuit, it's the other way around. In this circuit, what it does is that I can't count no more. I am about to go back to 0. Interrupt. See that? One is an overflow circuit. The other one is a compare circuit. All right? Now check this out. Check this out. It doesn't matter what value you pick for CCPR1. It really doesn't matter the value you pick. If you fix that value is a fixed number, the mathematics that dominate this CCP circuit is going to be exactly the same as the mathematics that dominate the overflow circuit. You see that? So I can sell you the behavior and I can implement it either with an overflow or I could implement it with a CCPR, all right? So that's where we're gonna go. So I put a couple of slides there for you so that you can remember. So we got that the interrupt triggers when the value of the timer and the user provided CCPR are the same, right? When these two values are the same, we're gonna trigger. And there is two modes. There is the fixed CCPR mode, and that's where I wanna start you, okay? So let's go with the fixed CCPR. A fixed CCPR scenario, so here's scenario number 1, fixed CCPR values. This scenario is when you, the user, pick one value. All right? So you come in your software, and there is one spot in your software that you're going to take a number and you're going to deposit it inside of a CCPR, but only once. This will never happen ever again in the life cycle of that software or the execution cycle of the software. So while the software is executing, you will only change this value once. You will never do it again. If that is the case, right? Now listen to me carefully, because this is what happens in the test every year. If that is the case, if you identify that this instruction where I put a value in CCPR happens only once, right? The mathematics that follows now will be operating, all right? So it goes like this. Imagine that you have kind of like a time sequence. And so this is time 0, and these white lines determine the behavior of your timer, right? So the timer is going to start counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what timers do. They behave like clocks, right? So every time you hit 2 to the 16 minus 1, timer 1 is a 16-bit counter, right? Every time you hit 2 to the 16 minus 1, on the next count, an overflow event is going to happen. So these vertical white lines represent overflow events, right? If you leave the system alone and you do nothing with the system, what's going to happen is that you're going to have overflow events every 2 to the 16 counts, right? Starting at 0, end up at 2 to the 16 minus 1. So every 2 to the 16, I'm going to have one overflow event inside of my microprocessor. I know that that's true, right? Make sense? Okay. What if now I pick a value for CCPR? Notice that the position of CCPR with respect to 0 is exactly the same on both sides of the overflow. See that? So let's say that I pick the value that looks like almost 40% of 2 to the 16, right? Just some value, really doesn't matter. What really you have to observe is the fact that the amount of time that it takes for this CCPR to occur the first time is equal to CCPR, right? So if you pick the value of 10, it's going to take 10 clocks, 10 timer 1 clocks for this event to happen the first time. You here with me? So the user picks that green number, and I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and eventually I go, I saw it. And this green arrow represents a CCP interrupt. See that? After the CCP interrupt occurs, the clock will continue counting in its merry way, an overflow will occur, and I will continue counting again until I hit that number one more time, right? My contention with you is that I believe, and we can prove, that the amount of time between CCPR events is equal to 2 to the 16. Can you see that? And it really doesn't matter when I choose my CCP. You can choose your CCP to be like 1. From 1 to 1 on the other side is exactly 2 to the 16 count. So, listen to what I'm going to say very carefully. The initial value that you give to the CCP system in compare mode is immaterial. It doesn't matter. I don't care the value you put in there. It doesn't matter. You can pick in here to be 2 to the 16 divided by 2. You can pick this to be 0. You can pick this to be 10. And the amount of time between green events is going to be equal to 2 to the 16. There's nothing you can do about it. See that? So the value of the CCP on a fixed system does not matter. So it means the following. The mathematics that dominate this is going to be this, and T of the CCP1 is going to be equal to 2 to the 16 times T1C. But if you notice the mathematics are exactly the same as my overflow system. You see that? So what that means is the following. There has to be a different way for me to exploit this compare mode. If you simply take the compare mode, you turn it on, and you give it one single value, you're doing nothing different than if you're using some sort of an overflow system, right? There has to be a different way. Okay? So in the next slide, I kind of like give you the idea that the distance between these events, our CCP interrupt, is supposed to be equal to 2 to the 16. And that's how your math is going to look like. Okay? Make sense a little bit? All right, now here's the deal. This T of the interrupt, you can call this T of the interrupt here. It's a CCP1 interrupt though, right? It's T1C times 2 to the 16. Now let's go to the actual event that I really want, because this is the event that compare mode is actually used 99% of the time. By the way, let me just give you the code first. The code is actually really simple to set up a compare mode. The capture and compare circuits in general terms are very easy to deal with. One thing to keep in mind, you should put a little note in your notebooks, because the capture interrupt and the compare interrupt vectors are exactly the same vectors. It's the same circuit that is actually alerting the user that this is going to happen. So if you take a look at powerInt CCP, that is your interrupt vector for the capture mode, but it's also your interrupt vector for your compare mode. See that? It's exactly the same. So let's go over that code slowly. So I want you guys to open your data sheets and go straight to the capture and compare module. I think that that's going to be on page. Double check that for you. Give me 1 second. It's chapter 15. I'm going to open the PC. Let's see. There you go. So here's a data sheet for the capture and compare module. This is the CCP1 con circuit. I want you to read a couple of things here for you. And here is something interesting about the compare mode that I need you to just pay attention to, because compare mode is oftentimes used in conjunction with an external event. Well, listen to what I'm going to say now. It happens that when you use compare mode, it is very common for people that are using compare mode to create an external event. It means that I will toggle a bit somewhere. And it's part of like 99% of these applications tend to look like this. So what they did is that this particular circuit has a compare mode together with an output toggle on match. See that? There is an output toggle on match. And so what this means is that when the interrupt happens, I will not only interrupt the circuit so that you can do something about it, they will also toggle a bit. All right? So please remember that for CCP1, pin C2 is the pin that actually is physically connected to field this behavior. So when CCP1 in compare mode interrupts, and you choose the compare mode to be equal to 2, you're going to get an output toggle on pin C2. Okay? And so that instruction will be something like this. CCP1 con CCP1 MX, or CCPXMX, I think it is. I don't know how I did it in the library, but if you do this, this is interrupt with toggle. With toggle on C2. Okay? So this is an interrupt with a toggle on C2. If you take a look at your options, you can choose in there to have the number 2. You can have 7, 8, 9, 10, and 11. Those are all your different options for compare mode in general terms. just to give you a little bit of an idea, we use compare mode a lot to generate signals that they look like PWM, but they have variable power. So instead of having power that is equal to 5 volts, if you want to vary your power from 0 to 5, 0 to 3, and then change the frequencies of those and the duty cycle on those, these compare modes is what we tend to use. And so we created a pretty cool application where we take medicine that goes into a chamber, and then we'll just create plasma inside of the chamber to actually change the chemical composition of that gas, and then deliver that gas in the lungs of children in intensive care unit. And so we were using 4 of these timers operating together to create variable amplitude, variable frequency across a specific amount of time. So this is a very, very, very useful skill to have, understanding how these little guys work. And they're very easy. We'll show you in a little bit the application and how this works, okay? So this is step 1. Step 1, you gotta just make your system become a compare mode, okay? So this is while you have...
It's flipping, hold on.
No problem. This is why you have instruction 1 here.
Should be up now.
All right, so this is why we have CCP1 con CCP XMX equals 2, and then you pick one of these values, 2, 8, 9, 10, or 11, depending on what you want to do with it, okay? And so that little x is just one of these numbers, okay? Now, once you do that, your CCP circuit is ready to go. So now I am in compare mode already. Step 2, you have to make sure that your PIE circuits, this is your interrupt. So your interrupt is located in PIE, and the circuit is called CCP1 IE. And then you have your global and your peripheral, and that sets up your interrupt circuit, okay? There's one instruction that I have missing here. And the instruction that's missing is that you have to turn on timer 1. And so that timer 1 is T1 con arrow TMR 1 on equals 1, right? We already have a structure for timer 1, so I'm not going to spend time explaining how that structure works. I hope that you guys already have it and understand how to use it. And there it is. That's it. We don't need anything else. Now, listen to what I'm going to say. Write this down somewhere in your notebook. Check this out. If you choose your compare mode with a 2 input, that means that even though there is nothing here in your interrupt application, pin C2 will toggle every time this guy interrupts. Because it is a compare with a toggle. It will do it for you. All right? You don't have to create a physical toggle in here. All right? That's the important idea behind it. By the way, if you actually see how LEDs in your PCs actually behave as if they're a heartbeat, or they fade away, they have this fade and he come back and he fades and he come back, or how do they do it? Compare mode. They just simply use a compare mode and they switch around the values of CCPR to create a breathing or a fading LED effect. That's how they do it. So we'll show you. You're going to be doing it as a lab. I know you're all excited about this. It's not that hard. You'll see. It's fairly simple. Okay? Any questions on this? So this is minimum necessary conditions to get your CCP to work. Make sure that you add this instruction to it. In fact, I'll add it before loading this online. So I don't want to. So I'll add it here. To make sure that timer 1 is on. And that's it. That's all you need. System's ready. All right? Okay, now, here we go. This is the actual application I wanted to get to. This application is the variable case scenario, and this is the scenario that you will use probably 99% of the time, right? If I am not going to use the sliding case or the variable case scenario, I never use compare mode. There's no point. I put an overflow and I get it over with, right? So this is the variable case scenario. The variable case scenario begins very much the same way. We have timer 1 operating on its own. We have your overflow events. But this time, we have, come on. But this time what we have is events that are actually in very close proximity with each other. Instead of having a fixed value, every time that one value triggers, we change the value of CCPR to gain just a smaller gap between those green events, those CCP events, right? How do we do that? The accumulator from embedded. If you remember in embedded, we have this instruction. It was CCPR1 equals CCPR1 plus a new value. Any value. Just call it a jump, call it new, call it whatever you want to call it. But that was the value. It was sum equals sum plus x. You remember that? Sum equals sum plus 1. That's the stuff that we were using in embedded all the time to try to figure out what is the average of a whole bunch of numbers. So you will go exam equal exam plus new exam, and then when you were done, you will divide it by. Or if I want to know how many clients per hour are going into a specific store, you just go x equals x plus 1 plus 1 plus 1 plus 1, and then you divide it by the amount of time, and then I give you the average per hour, right? That's the idea behind it, okay? So here's the deal. Now think about this carefully. The starting value in the variable case is also immaterial. It really doesn't matter. It's the same concept as the traffic light that you're about to encounter started on a green or a red. Does that information matters? And the answer is no, it doesn't matter for my use with the traffic light, my interaction with the traffic light. Does that make sense? The same thing is going to happen here. You're going to notice in the code that we're going to share with you that my starting point is going to be given, but listen, it's completely immaterial for any mathematical calculation. It doesn't matter where you start. Eventually, after the system begins the life cycle, this life execution cycle will now take a life of its own, regardless of the starting point of my circuit. All right? So here's what's going to happen now. The value that I choose as a new value, this little new value in here, is going to determine the width of my interrupt. In other words, it's going to determine the period of my interrupt. If you choose this to be 30 counts, that means that your interrupt is going to interrupt every 30 counts. If you choose this gap to be 41 counts, it's going to interrupt every 41 counts. And I have 2 to the 16 to do this. You see how accurate I can be now. Instead of having 4 prescale values, now I have 2 to the 16 values. Not quite. You have 2 to the 16 minus about 72 cycles that it takes for the interrupt to really take place. So, but in general terms, that's what's going to happen. So, this is the number of counts between CCP1 interrupts. See that? So here's what happens. Every time your machine interrupts, you're going to start with one given value. It doesn't matter what your starting value is. It doesn't matter what your starting value is, right? I can put there 3,000, 4,000, 5,000, 7,000, 60,000, doesn't matter. What's going to happen is that after the first one interrupts, at the moment of interrupt, you are going to take the value of CCPR and you're going to change it to a brand new value based on a shift. This new value is just a shift in counts. So let's say you start at 1,000, and I want to go every 100 counts. So then you go 1,000 plus 100, it's 1,100, right? So I have 1,100, and that's my new value. So the machine hits at 1,000, and it's not going to be able to do anything until 1,100. When it hits 1,100, I add another 100, and it becomes 1,200, and so on and so forth. So all of a sudden, you just change the granularity of your system. Your system is going to start interrupting way faster than before because I have full control on how often I want this guy to interrupt. You see that? So the mathematics are going to change a little bit. They will look like this. Your interrupt your CCP1 interrupt now is going to be T1C times or plus T1C times, sorry, that jump. That should not be a plus, that should be a times. So it's going to be T1C times the jump, right? Because T1C tells me how many of those, how much time it takes for every count to happen, and then the jump tells me how many of those counts I'm going to have. See that? So here's the change in code. The code looks exactly the same way. There's your CCP, there is your 3 values, there's a timer 1 that we forgot in here again. There is your starting value. Once again, the starting value really does not matter. The only reason, and I think this is more intermediate level programming, I'm going to say it out there, you don't have to remember this. The reason why sometimes we have a starting value is because I want to synchronize this with something else. So when it comes with synchronizing, I can actually choose my starting point so that I can get my circuits synchronized. But in general terms, what matters is this instruction up here. The value that shows up in that plus sign will determine how often the circuit will interrupt. See that? So a beautiful place for this, like I do this in exams all the time. I put 3,000 here, and then I put 1,000 there, and then I just watch it happen. Somebody's going to use that 3,000 from down there to do something with math. The initial value in compare circuits is absolutely immaterial. It does not matter. You should never even look at it. It doesn't matter. Does that make sense? All right, let's do this. Let's do it together. So let's try it. The beauty about compare mode, now that you guys are at this point, is that in capture mode, we actually added everything we needed into our library. So our library is complete. There is nothing we need to do. So here's what I'm going to do. I'm going to just give you a basic circuit so that you can actually see the circuit operating. And then that's what you're going to be using for your lab. I think it's in 2 weeks. We're going to have a lab where you're going to create the fading effect. So the fading effect is you're going to have an LED, you're going to have a microprocessor on it, and then it's going to just go up, and then it just fade away with only 5 volts and 0 volts. And we're going to be doing it with this, okay? So you'll see it. All right. So let's get to the PC. And then let's just do a compare mode together, okay? So I'm gonna get my Pixie. So next week we're gonna be doing pulse width modulation, and then we have a test the week after, okay? So we're just gonna make a new. So I'm gonna create a T1 compare. Make sure that I got this. And so I'm gonna go compare test. Just do the preamble, nothing special. Let me double check if this is still working. It is. And then Let me get my interrupt going. Nothing here. This is a compare with toggle. I'm gonna add something here because I think it's, you get used to this kind of, when you get used to this kind of work, you want to be very explicit. I want to make sure that I make that C2 an output. So it's just kind of like, if I'm going to be using C2 as an output, I'm going to force it to be an output, right? It's going to make very explicit about it. And so that's that. And then I'm going to turn timer 1 on. So I go T1 con, and they go TMR1 on. And then it's just a matter of now finishing the interrupts. So this is CCP1 IE equals 1. And then the global on the peripheral. So that's it. So we go incon PEIE is 1. 0. Incon GIE is 1. And we're done. This is while 1. This should get the system working. All right. So remember, this part that you're working right now is just the recipe, right? Every time that somebody goes, use a compare circuit, that boom, that's the circuit that will come out. This software will come out every time. So we're not doing any kind of application right now. This is just plain out setup stuff. Let me put comments in here so that when I post this online, you have reference. So this, the reason we do this is because I want C2 as an output. This one is turn timer 1 on. That forces the prescaler to be equal to 1. This is the CCP1 interrupt enable. This is a peripheral interrupt enable. And this is the global. There. All right, so I'm going to leave this here on the side, and then we're going to open now Proteus. We were approved the new version of Proteus, so probably they're going to buy it. It's not going to affect you guys because it's going to take a while to process it, but we got brand new Proteus.
Maybe it won't crash for no reason.
Maybe we'll crash less.
Hopefully,
right?
maybe more.
Maybe it'll have a reason to crash.
Yeah.
Right.
Yes. I think that we, as part of the deal, we are making sure that they will give you guys free copies of the software for 1 year. And then after a year, the license will, every time you log in, the license will capture you and then shut you down. You will not be able to compile, but we're very close into getting Proteus to give us student licenses for like legitimate licenses. So that's good. Okay, so we know that C2 is going to be generating an output. So I just loaded the circuit from last week. I didn't do anything new, and I'm gonna just change this to the oscilloscope. I want this guy C2 connected to the oscilloscope. So I'm gonna call it oscope, and there it is. I am ready. I'm connected. This guy's connected to the oscope. So I'm gonna save this project as a compare mode, T1 compare.
into. Let's see.
So I'm going to take the compare test. I got two people competing for that line. So let me just find who else is connected to that line. This guy. So I'm going to get it out. Oh, there it is. So I'm going to trigger out of A. And so notice that my software has absolutely no toggles. The machine is doing it for me. So I'm going to take this, put this on the side, and pull the software again. So notice there is no toggle on C2. I never physically toggled it. I just simply know that the circuit is capable of doing, and I allow the circuit to do it for me. Always remember that as you guys mature in your microprocessor careers, make sure that you get to know your circuit and allow the circuit to do what it was designed to do. Don't do in software what a piece of hardware could do. You will never be faster, right? And so I think that that was the magic a professor of mine told me a long time ago, and I've been stealing that line forever. A very good firmware programmer is the one that makes the least amount of code. You make very little amounts of code. Just let the hardware do what it was designed to do. And so getting to know your hardware is extremely important. And this is why when you take a look at your software engineers programming in firmware, they look really funny code. It's like, what are you doing? You don't understand your hardware, don't you? So, by the way, you guys are in a very interesting position. Let me give you some news. Madison do not teach their students embedded systems. They are assumed to learn it on their own. Isn't that interesting?
Why is that?
I have no idea. I thought that they should be actually teaching it, but they don't. They just teach high-level stuff. Everything is high-level. So they're assuming that their students will pick it up on their own. I don't understand that. So I find it very, very interesting. I was reviewing their curriculum not long ago because my son is going there. So we were looking at what classes to take and all that stuff, and I just realized there is no actual firmware class. This is interesting. So anyway, that means that you have no competition for those positions. That's what that means. You see that? So let me just change really quickly the software here. This is the guy that is right now oscillating. If you want to do now this, I'm going to go here to CCPR1 equals. I'm going to go plus equals. And then I'm going to make here 1000. I'm not going to change the oscilloscope. Notice I'm going to leave the oscilloscope alone. Look what happens now. I'm going to just go stop and run. Look at the oscilloscope. What happened? It went from 2 to the 16 interrupts to create this beautiful long wave to interrupting every 1000. So now I have to just dial my time per division to zoom in. So let me zoom in. Check it out. I'm going to zoom in now. Here we are. But what's the difference? I'm interrupting every 1000 cycles instead of every 2 to the 16 cycles. So I went from one equation to the other. You want to double the frequency, right? I'm sorry, half the frequency. So you can come in here on your software and you say, you know what? Forget every 1000. I'm going to go every 1000 and every 2000, let's say. So you go every 2000, look what happens to it. Opens up. See that? You can do this every 500. So we can go to, you know what, maybe I should do this every 500. You see how much granularity I have? You can go every 501, every 502, every 503. Now the question is, what is that doing mathematically to my system? Let's take a look. Let's take a look. So let's take a look at the mathematical analysis. So when you turn on your timer for the first time and you do nothing to your timer, it actually goes into prescale equals 1. Always does, right? So T1C is actually 4 times 1, which is your prescale, divided by 20 megahertz, right? And the reason why I leave it at this is because we've done this calculation a bunch of times. This is going to end up being 0.2 microseconds per timer tick for every timer count, if you think about it, okay? So this T1C tells me how fast is the timer going based on my software. The next part is to figure out what is the period of the CCP1 interrupt. And this period is going to be the little jump value that we have in our software. So you look at your code, and so I go straight into this number. That's my 500 jump, right? So I'm going to do, this is going to be 500 times 0.2 microseconds. So this is going to be 1,000, right? So 100. So this is 500 times 2, and then you move the 0.1s, and then you put it 100 microseconds. So this is how often that CCP is going to trigger, right? Now, if you want to know how often or how much is the period at the oscilloscope, the period at the oscilloscope requires 2 toggles to create 1 full period, right? So that means that the period at the oscilloscope has to be 2 times this TCCP1. So this is going to be 200 microseconds. So if I go here, and I put my cursors, I'm going to put one cursor there. And the other one here. Right there. Look at it. I don't know if you can see it because it's very tiny, but that's 0 seconds. That's 198, and I'm not quite on top of it. If you notice, my white line is a little bit off. I couldn't quite get it with the mouse, but that's 200 microseconds. So if you take a look at my math, can actually perfectly predict what the oscilloscope will tell me. See that? And so when it comes to delivering devices to the Food and Drug Administration for like gas medicine, these interrupts are so accurate that they pass all the FDA testing. That's what we use these guys. I can adjust this now by just a little bit. What if I don't want 200 microseconds? I want it to be just a little bit more. Instead of 200, I want it to be 200.4 microseconds. What do? Oh, you want 200.2? So I come here and I do 501 there. So you want a little bit bigger. And there it is. Just a tiny bit more. So instead of 500, it's 501 times 0.2, which is going to change this value, which is going to change this guy by 0.2, 0.4. That's really what it's going to do. So you see the usefulness of this, right? Now, this is how you see it in class. The way that you actually see it in real life is the other way around. A client comes to you and says, hey, I need a microprocessor that generates a signal at that period. And then you work it backwards. See that? Like, for example, in real life, somebody comes and says, I need design a C program that generates a 1 kilohertz square wave. Right? So somebody comes in and says, just give me a 1 kilohertz wave. Why? I need it for something. Right? And so you're trying to figure out now which overflow I can use to generate 1K. So you start messing around with prescalers and you start messing around with all these variables and it becomes a pain, right? Or I can simply use compare. The moment that you want a 1K, I know that I have a lot of control over my compare module. So what I do is this. This is 1 kilohertz at the oscilloscope, right? So what you do is that you're gonna start working this backwards until I get to this number, right? So I'm gonna work it backwards until I hit that number. I'm gonna see what that number is. So if you want 1 kilohertz, so I'm gonna start with the period at the oscilloscope is 1 over 1 kilohertz. This should be equal to 1 millisecond. So I'm sitting here. I'm sitting right there. If you take 1 millisecond and you divide it by 2, you get TCCP, right? So if you want to know how often I need my TCCP1 to interrupt, that's going to be equal to 1 millisecond divided by 2. See that? So I'm working the problem backwards. So they gave me the 1 kilohertz. From frequency, I change to period. Once I have the period, I divide the period by 2, and I get the frequency or the period that my interrupt needs to interrupt. All right? So this is going to be 0.5 milliseconds. So this is going to be equal to 0.5 milliseconds. Okay? Now I'm here. I have this. This is this. I have that. And I already know this. So if you get TCP divided by 0.2 microseconds, that gives me my jump. So if you want to know what your jump should be, you're going to take TCP1, which is 0.5 milliseconds, divided by 0.2 microseconds. Okay? Be like 400, I think it's 4,000. My calculator, there. 0.5 milli, 0.2 micro. So 2.5. So this is going to be 2,500, 2,500, right? What does that mean? It means that if I just come here, if I just stop this, and I come to my code, and I put here 2,500, and I run this guy is a 1 kilohertz wave. And then you turn around and you charge them a lot of money for it. Make sure you charge them lots and lots for it, right? Think about it. For you guys, it's simple because you guys have been at this for about 1.5 years now. But for the rest of the world, it's not that easy. See that? Never underestimate how valuable you are for a company. You are very, very valuable for a company. Without you guys, we can't operate. We need you guys. So, a little bit of knowledge, a lot of impact. So, there it is, 1 kilohertz. You can do this for all kinds of applications. LED fading, you can do this for sound generation, beat generation at different frequencies and at different pitches. This is actually used for gaseous medicine delivery. This is used for making sure that we have countdowns. So if you have a specific event and you want to count down from 1 spot to 0 and then create an interrupt on that, that's how you do it. So this compare mode is the most versatile counter that you can find inside of your microprocessor. And so it gets used, these compare modes are used a lot. So there it is. But if you notice, this is what we always do in school. We teach you how the system works, but in reality, it always works backwards. Build me a system that and then you just work it all the way backwards until you find the number that you're gonna change your software so that it can generate the signal that you want. Does that make sense? Alrighty. Well, that's that. We're pretty much done. Make sure that you keep working on your labs. And then in 2 weeks, we have a test, okay? I'll be putting out there also a practice exam from the past so you can see it. All right?